All right, so let's go ahead and get started. The reason why I'm playing around with the screen up here is because I don't know if any of you guys have tried watching the screencasts. Anyone try watching those? It's pretty bad, right? And I'm wondering if it has to do with the way that I'm actually projecting this. Because right now I've got a wide screen versus a not wide screen up there, and that may be part of the issue. But I can't seem to fix it right now, so we'll see what it looks like if you're looking at the screencast. But screencast doesn't look very good for the past few lectures, and I'm trying to figure out what it is. The first lecture it looked fine, but these past few lectures it just did not look very good. So we'll figure it out one of these days, but I think for this lecture we may not be able to figure it out this time. I'm just going to do what I did last lecture, which is this. I think it looks fine up there, right? But just when it screen captures it, it may not do a great job of it. All right, so announcements. Okay, so I'm not going to have any office hours on this coming Monday, mainly because I'm traveling again, but I should be back by Tuesday. So I'll be all the way on the other side of the nation in Washington, D.C. I should be able to fly back, though, and be here back by Tuesday. If you see an email, though, that says I'm not back, then you know if there's weather or something that prevented that flight. So just letting you know, there will be lecture Tuesday, unless you see an email. Any other thing we should take care of? Logistics? Anything? Okay, so I'm sending emails to the class every now and then, like this makeup lecture that we had before. I guess there were some people that sent me emails also saying, wait a minute, where's the makeup lecture? Why weren't you there on Saturday or something like that? And so I'm sending the emails to people who are registered for the class. But if you want to get on that email list, I basically take that email list off of the sheet that I know people are registered on. If you want to get on that email list because you're sitting in or something that I don't know that you're sitting in on the class, you probably want to send me your email and ask me to add you to the email list. So that when announcements are made for this class, you'll get them too. Okay? All right, so last time we were looking at active loads. That's the last thing we were doing. And we were looking at the types of active transistor loads, and we were analyzing some of them just to make sure we understand them well. And so we'll finish doing that, and we'll actually take some circuits that are actively loaded and analyze them for gain and impedances and frequency response. And then after those examples, we'll start looking at current sources, which I understand is a topic that you've had to some extent already in 105. So I'm going to start doing this topic at least using pre-written stuff. But then when we get to the stuff that I think you don't know yet, we'll slow down and we'll do it by hand the way that I'm usually doing lectures. Okay, so last time this is what we did. We sort of said there's a number of different types of active loads you can have. There are diode-connected active loads, like are shown here, this diode-connected enhancement load for this NMOS transistor. This is assuming the load is on top and the driver is at the bottom. Depletion load, which is sort of an ancient concept that no one really uses anymore, so you don't really even have to think about that. Diode-connected PMOS load, which is another popular type of load that people use. And then finally, a PMOS current source load, which is something you will see most often for MOS or CMOS type devices. We analyzed one of these, which was this diode-connected enhancement load, and we were able to analyze it fairly quickly because if we looked up in this direction, just by inspection, the gate of this transistor is grounded, the drain is grounded, so this is something that we can inspect, analyze very easily. Right? Initially, it looks like it's in feedback, but it's not in feedback because everything's grounded. And so just doing straight inspection, we get the resistance seen looking up into the source of this transistor as being 1 over GM plus GMB. That's just one of your inspection analysis formulas. Okay, and so from this, we can kind of conclude that when you see something like this, it looks like this is a diode connection of a transistor, right? Because in the end, this 1 over GM plus GMB, that's the impedance you see looking into a diode. And it turns out, as we'll see, that that is indeed going to be true. Anytime you see a connection like this or a connection like this for a bipolar transistor, that's equal to a diode. And in fact, when they implement diodes in a bipolar technology and in an MOL, mainly in a bipolar technology, they will implement it like this, with a bipolar transistor with the base connected to the collector. Okay? Now, last time we started taking on a different problem here, and that's still with this transistor, this MOS transistor, sort of in this diode connection. But we didn't want to just do an inspection analysis of this because this is actually in feedback here. Right? If you look at this transistor above, if this is all going straight to VDD, that's not in feedback because these are all grounded. Right? In the AC small signal circuit, these get grounded because they're attached to VDD. In this circuit here, where I've now taken that same connection around this MOS transistor, I'm now tying this end to some resistance. That's, of course, no longer ground. And so, because I've got feedback in this circuit, I probably don't want to inspect, analyze this, because, I couldn't really use my inspection formula so directly. Turns out you can sort of inspect, analyze this. Maybe something we'll do a little later on when we look at this again. But at least from last time, we went ahead and brute forced this. We went ahead and recognized, okay, there's feedback here. I don't want to use inspection for this feedback, so let's go ahead and pull out the complete small signal circuit for this, including the hybrid pi model, which you see drawn here, which is what we did last time. And we went ahead and did an analysis. We put a test voltage source, this Vx right here, and drove it to create a test current source, and are taking Vx over Ix to figure out what that resistance, I'm calling Rs, is, looking up into this source. And we did the analysis last time, and we ended up with this as the result. And so the result is basically that you still see this diode-like behavior from this transistor because its impedance is 1 over Gm plus GMB. Okay, but then you add to that this resistance R sub D divided by 1 plus eta, where eta is that parameter that you saw in the first week of lecture or so when you covered MOS physics or so. Eta is just a definition. It's defined as GMB divided by GM. Okay, so in general, it's going to be pretty small. What approximately is GMB over GM? Just sort of, what's that? 0.3? Yeah, somewhere from 0.1 to 0.3, something like that. 0.3 is kind of big, but 0.1 or so, 0.2, maybe that's what you'll end up with in most of these circuits. And so that's going to be a pretty small number, but maybe not completely neglectable, right? Because like I said, if you're within 10%, you're right. A lot of times if you're in 20%, you're right. And if this is 0.2 or 0.3, that's a little beyond 20%, right? So sometimes you have to take that into account. And so that's why I'm leaving that in there. Most of the time what you're going to do is just say, okay, that's 1 over GM plus RD, looking up in that direction. Okay? So you'll make that approximation many times. So this is the case where we're looking up to the emitter of this device here, and the resistor is on top. Okay, there's, of course, the other case where we're looking down on the device from the top. So the other case here is this one. That's still in this sort of what we're calling a diode connection. And now my resistance is this source resistance looking there. And now I'm interested in what this resistance is, R little d, that we've been calling it, looking into the drain of this diode-connected transistor. And for this, you could set this problem up the same way. You want to drive that with a Vx, measure the Ix going through that. To be complete about this, you probably want to draw the complete small signal circuit, which again is going to be this hybrid pi-based circuit, where I've got Gm times VGS as a transconductance. There's my VGS there. That's my gate. This is my source. I'm going to have, as usual, the GDS conductance that's associated with R naught. Here's RS. There's the source S. And then finally, because it's an MOS device, I have this GMB times VBS, and B is right here, grounded, we're assuming, and we're driving this from the top, from VX, measuring IX. Okay, so we could do the analysis here. This time I'm not going to do the analysis. I'm just going to say you do the analysis. And I'm just going to give you the result that you end up with after doing this analysis. You end up with this R little d, which again is Vx over Ix, is equal to 1 over Gm, not 1 over Gm plus GMB, but 1 over Gm because we're looking at this from the top. That should make sense to you. Plus 1 plus this eta factor again times the resistance Rs that we see there. And this is about equal to 1 over Gm plus Rs, depending on what that eta is, right? If eta is about 0.1, then it's about equal to that. If it's 0.2, then maybe not. But in the end, what you're seeing is that anytime you see this, you can pretty much equate that to a 1 over Gm, okay, from the top. Over a 1 over Gm plus GMB from the bottom. And it doesn't matter if you've got a resistor above it or a resistor below it, if it's in series with those resistances. This is pretty much what you end up with anytime you see this connection. Okay? So that's just something to remember, and I think that's an easy thing to remember. Whenever you see that connection, it's equal to a diode, and a diode's equivalent series resistance is 1 over Gm, okay, which we have done through complete derivations with the small signal circuit. All right, so with that and knowing that, let's now just apply this to some circuits. So let's apply this to a common source circuit, meaning that we're just going to take this MOS load here, and put this directly over a driver MOS device. So M1 is the driver, and M2 is the load. And so as usual, we're interested in the gain of this particular connection here. And so to get that gain, well, I know the gain is going to be minus Gm times whatever the load is that I see at the output here. Okay? And like we just said, if I look up in this direction, I see a 1 over Gm2 plus GMB2. So that's what I see looking up in that direction. So to write out the gain here, actually I want to call that A. So my gain, A sub V, which is V naught over VI, that's going to be minus Gm of 1 times all of this resistance looking up in that direction. Now there is an R naught right here that is in parallel with that, but I'm going to go ahead and neglect that, because it's going to be much bigger than 1 over Gm plus GMB. But this becomes Gm1 divided by Gm2 plus GMB sub 2. Okay, that's my gain expression, that simply. And using my eta factor, I could say that this is also equal to minus 1 over eta plus 1 times Gm1 over Gm2. And beyond this, then, I can also plug in the actual values for Gm1 and Gm2. So A sub V then becomes minus 1 over eta plus 1 times, what's Gm1? That's the square root of 2 times mu n Cox times the W over L ratio of device 1. times the current going through this, and both of them have the same current. And so GM2 is 2 mu n Cox times W over L2 times that same current. You can see from this expression that a lot of things cancel out. All of those things cancel out there. And we end up then with this being equal to minus 1 over eta plus 1 times the square root of W over L1 divided by W over L2. That becomes our total gain for this. And so you can see how simple it is now when you're using MOS with an enhancement load diode connected NMOS device to specify whatever gain you want. To specify the gain in this situation, all you do is ratio the W over L's. Okay? So if I wanted a gain of 2, I would just make this W twice as big as that one. Now that's going to be modified a bit by this eta here, depending on how big that eta is, depending on how big GMB is versus GM. But all in all, it's going to come down to this, right? Pretty simple stuff in the end when you plug in all the values. Okay? Let's do one more example here. And so in this case, let's do a diode-connected PMOS load. So in this case, all we're really doing is turning around the transistor. So in this NMOS load, yes. You mean M2? Okay. Yeah, we're about to do that problem very soon. So I'm about to put something that's not diode connected above that. Not now, but the example after this. Okay? All right, so let's now do the diode connected PMOS load. So in this case, it's going to look like this. Here's my VDD. And I now have a PMOS transistor. And usually for PMOSs, where's the well or the bulk of a PMOS tied to? It's going to VDD, right? So it's going to the highest voltage source you can find in that circuit. And so there it is. It's going to VDD, which means in this PMOS, I'm tying my source to my bulk, okay, which simplifies some of your inspection analysis equations for this. But this is diode connected like this. And I've got that above my NMOS device, which is going to ground. And with NMOS devices, right, their wells or their bulks are tied to ground. And so this becomes my circuit. And so now, if I look up into this device, and let me draw my V0 a little lower. So now I'm interested in what that resistance is looking up into that device. Again, looking down, I do have this R0 of 1, which is a huge resistor looking down in that direction. That's usually going to be a mega ohm or something like that. Okay, but looking up in this direction, what do I see? Yeah, I see just a 1 over GM there from that PMOS device. That's 1 over GM2. And so I can very quickly write my gain expression here as being minus GM1 over GM2. And if I plug in all of those same values that I plugged in down here for the previous example, for the GMs, I'm going to end up with minus square root. And now I have to keep the mu's because I have an N-type device and a PMOS device. They're not going to have the same mu n and mu p. So this now becomes mu n times W over L over 1 divided by mu p times W over L sub 2. And that very simply and very quickly is the gain of this stage. Okay? And you can see how simple it becomes in the actual design again. You just have to now account for whatever the mobility is of the N-type device versus the P-type device. As long as you know that ratio, you can still design your gain just based on how big the N-type W is versus the P-type W. Okay? Gain, very easy to specify. Okay, so let's go on to another example, and this is with the PMOS current source load. So exactly the example that you wanted to see. So in this case, again, I have my PMOS transistor. Its well is still tied to VDD. But now, instead of tying its gate to its drain, I'm now tying it to some voltage, which I'll call V bias. Okay, so that V bias has to be generated by something. Some circuit has to generate that V bias, and we're going to spend a lot of time looking at circuits that generate that V bias in the next part of lecture. But for now, right, we're really looking at this circuit here. And so in this case, if I look up in this direction, again I want the gain, looking up in this direction, I see an R0 for for the PMOS device, which I'm just going to call, I'm going to do it in conductances because the equations look a little easier. That's GDS2. Actually, the equations don't look a little easier. I'm just doing it for fun. Right, so this GDS2, which is equal to 1 over R0 of 2. Looking down this way, I also see a conductance, GDS1, which is 1 over R0 of 1. And so I can express my gain, A sub V, which is V0 over VI, as just minus GM of 1 divided by GDS of 1 plus GDS of 2, which I can also write, if you insist, minus GM1 times R01 parallel with R02. Okay, so very simply that becomes the gain of this. And one thing we can see, whereas these other gains were fairly well controllable by the W over L ratios, this gain is not as controllable, but the gain is huge. And that's because the R0 of each of these transistors is normally huge. Okay? So that's a reason why this is a more popular circuit than the other circuits that I just showed you. Okay, the circuit that has this enhancement load, diode-connected NMOS device, or this diode-connected PMOS device up here, these are circuits that are used, but they're not nearly as popular as this circuit down here, because this circuit down here gets you tons of gain. And after all, if you're making an amplifier, you're generally looking for tons of gain. Okay? Now, that's not always the case, because as we'll see later on, that gain and bandwidth sort of have a constant product. And so if you're looking for a very high bandwidth circuit, you may tend to use these diode-connected loads rather than this PMOS-connected loads. Okay? But if you have a high gain, lower bandwidth circuit, you'll use this case where you have the PMOS not in a diode connection. So the gain is huge, but this is more difficult to design because it requires this V bias voltage right there. Okay? And again, by the end of this lecture, we're going to be talking explicitly about how to design these V bias voltages. But before doing that, let's just go ahead and take a look at some actively loaded MOS inspection analysis problems here. So just a few little exercises to do. So first example, let's do a multi-stage actively loaded MOS circuit. And let's look at this circuit here, where we're going to have a first stage that uses a PMOS loaded with a V bias generator at its gate, a PMOS loaded NMOS common source amplifier. So that's M1, that's M2. And this then is going to drive an output buffer-like circuit, which is a common drain circuit. So also using a NMOS load here that's not diode connected, so has a V bias. I guess I have to call this V bias 2 and this V bias 1. And then we'll take our output right here. So this will be M3 and M4. It's NMOS. So this is actually a common drain circuit. So I want it to drive small loads. Oh, I'm sorry. Yeah, that's its arrow right there. Okay, so what do we want to do? We want to do the generic things that we always do with these amplifiers. So the first thing I want is the input resistance. And input resistance will be right here. And I got some questions in office hours about how you define input resistance and et cetera. I guess in these homeworks we should have drawn little arrows to show you exactly what resistance we were looking at. But in general, what you do is you identify what's the amplifier and what's not part of the amplifier. So usually when you have a source that's driving the amplifier, that source always has a source resistance. And so a lot of times if you see a source in an RS, that's not part of the amplifier. And so we're interested in what the input resistance is going from that point of that source resistance to whatever's to the right. Okay? So that's how we generally define input resistance. Also, if I had a load resistor out here, then we would define the output resistance before that load resistor, because that load resistor is not considered part of the amplifier. It's considered part of the next stage. Actually, for that load resistance part, it's a bit ambiguous there. So to really do it right, and on any exam, I would always give you a little arrow thing like this, bracket arrow, that tells you exactly which resistance we're looking for. Okay, and we should have done that in the previous homework to make it absolutely clear for you. Okay, so what's the input resistance? It's infinity, because it's MOS, right? What's the output resistance? Looking in that direction. So what do we have here? So this device here is, of course, its source is not connected. So it's like this. This device, its source is connected down there to the bulk. And so if we were to look in this way, what do we see as output resistance? What's that? Yeah, you see an R0. There's an R0 coming from M3. But it's going to be parallel with whatever you see looking up that way. Okay, and if you remember your inspection analysis formula, what do you see looking up that way? Yes, so 1 over GM of device 4 plus GMB of device 4. Is that it? Yes, that's it. Right? You have some resistance looking this way. Right? And in a bipolar case, you'd have to take that resistance divided by beta plus 1. But in the MOS case, beta is infinity. Right? So any resistance seen looking back from the gate is going to be zeroed out. Okay, so this then becomes what it is, and really, right, since RO3 is enormous, it becomes this. Okay, so we got input resistance, we have output resistance. And so what are we looking for next? Naturally, we want the gain of this thing. And so let's go ahead and get that gain. And so for gain, let's do the same tricks. I mean, it's the same procedure that we've always been doing. So I have to define nodes. Let's define this node as node 1. That's node 2. The output node is node 3, although I may not use that because I may just use not for the output. And so the gain A sub V is going to be the gain from V sub S to V sub 1. That I can write as V sub 1 over V sub S. Times the gain from V sub 1 to V sub 2, which is V sub 2 over V sub 1, times the gain from the output V naught, from V sub 2 to the output V naught. Okay? So I need to calculate all of these different gains, and so let's do that one at a time in real time. So what's this gain V sub S to node 1? It's just 1. right? Because there's really no loading here. You got infinite resistance looking into the gate of the MOS transistor. So that's a voltage divider into a shunt resistance that's infinity. That gain is 1. Okay? And so now what's the gain of this second stage? And again, we get the gain taking into account the impedance from the next stage. But the impedance from the next stage is infinite, right? So it makes our problem much easier. So what does that gain become? Minus GM1 times 2 R naughts, right? If I look up in this direction, I see R naught of 1, sorry, of 2. If I look down in that direction, I see R naught of 1. And so I have R naught 1 parallel with R naught 2. And I cannot neglect any of those R naughts, right? Because they're both large resistors. There's nothing a lot smaller than them that makes them, that negates them, right? So I have to keep both those R naughts. And I like this a lot because that means I have a lot of gain in that stage. If R naught is 1 mega ohm and GM is on the order of 10 to the minus 4 or something like that, that's a lot of gain in this first stage. Okay, and then finally there's this third stage. What's the gain of this third stage now? Guess I'll have to go down here. Anyone remember that expression? Yeah, it's GM times whatever resistance on the source divided by 1 plus GM times whatever resistance on the source. Or actually, 1 plus GM plus GMB times whatever resistance. So in this case, to write this out, I'm going to have GM of 4 times, what's that resistance on that source? Well, I'm looking down this direction here. That's an RO of 3. Okay? Is that it? Okay? Actually, there's another RO here. RO of 4 is right there. Right? RO of 4 is right there, and this is VDD, which becomes ground in the small signal sense. Right? And so you actually have to take into account that RO4 too. So in essence, this resistance is RO3, yes, but in parallel with that RO4. Okay? So remember, usually we neglect that RO4 because usually it's in parallel with a 1 over GM. But in this case, right, in that formula, we're not looking at, you know, the resistance at that node. We're looking for this resistance here. That's the RS that we're looking for when we use that inspection analysis formula, GM times RS over 1 plus GM plus GMB times RS. Okay? So the RS you're looking for is all the RS that's not going back into the source, but that RO3, or RO4, sorry, is not going back into the source, right? That RO4 goes from that node to the drain, which is grounded. Okay? Any questions about this? This is a tricky part that you should just know. Once you see it once, you'll be able to do it again and again. But just don't make the mistake of neglecting that, because you can't neglect it. They're both enormous resistors. Okay? And so this then divided by 1 plus GM4 plus GMB4 times RO3 parallel with RO4. Okay, and so in the end, I can rewrite this. This is okay as the gain equation, but I can sort of rewrite it in simplified fashion, where A sub V is minus GM1 times R naught 1 parallel with R naught 2 times this other parameter here. But what can I say about this other parameter? So I have GM4 times that, I have GM4 times GMB4 times that, and I have a 1 right there. Yeah, the 1 is a negligible thing compared to all of this thing, so I could do that. But then if I do that, then these two sort of cancel each other out. And I end up now with just a much simpler equation, GM4 over GM4 plus GMB4. Okay, and that now becomes my expression for gain of this actively loaded MOS multi-stage amplifier. Okay? And so you should be able to do these things, again and again in your sleep. Right? You should be doing it in your sleep because, like I said, practice makes perfect on these things. So get a lot of practice on this, right? I'm actually going slower than I should be going right now because I'm trying to explain everything that goes on this. When you're doing an exam, you should be able to just cut out these equations in a matter of, I would say, 5 minutes for this. Right? Just to get the gain. It should take you literally just 5 minutes to do this, especially for MOS where you're not worried about loading from the next stage because the load from the next stage has infinite impedance usually. Okay? So get comfortable doing these things and get comfortable not only doing what I just did, but get comfortable doing what we're going to do next, which is the high frequency analysis of this. Okay, so let me cheat here. If you're taking notes, start redrawing this thing because I'm going to cheat and just copy it. But don't worry, I have to do a lot of erasing too, so maybe this copying is not really any better than redrawing it. But let's do high frequency analysis, and so now I got to erase all this stuff. Actually, you're probably finished drawing it by now, right? Whoops, I lost the device. All right. Better save that. Sounds like something's going wrong with my computer here, so. Okay, so there's our circuit again. We want to do the high frequency analysis, and that just means we need to get all the time constants that are associated with each of the capacitors we can identify in this circuit. So let's start identifying capacitors. And so same procedures we've always been using. So there's CGS1. To be absolutely complete, I can draw that I have a CSB1 right there. I have a CGD1. I have, hanging off of this from M1, a CDB1. From M2, I have hanging off of this as well to ground, a CDB2, so drain to bulk capacitance for 2. I have a CGD2 right here. I have a CGS2 right there. And I guess I can draw here another capacitor to be complete, CSB of 2. And so I'm just basically putting capacitors, the same capacitors again and again for all of these different devices. So here, CGS3, CDB3, CSB3, CGS4, CGD4, and finally CDB4. I guess I also have here a CSB4. Okay, it's getting crowded with capacitors there, right? So the first thing we want to do is eliminate capacitors that we're probably not going to need. And so this capacitor is grounded on both ends. We're not going to need that. This VDD, as I'm drawing there, is actually ground because we're going to the small signal circuit. So this also has ground across it. We're not going to need that one. Same thing for the CDB4 right here. it's also going from ground to ground, so that's not going to have any bearing. And the CSB3 is not going to have any bearing on our analysis either. Okay? So those are the capacitors that I have to care about now. So now that I've identified those capacitors, I now have to go node to node and create time constants for each of those capacitors. But before doing that, well, let's start with node 1 here. But for, yes?
For V bias 1 and V bias 2, are we assuming those
Oh.
also know?
Yeah, I forgot to say that there. So V bias, these are DC voltages, V bias 1 and V bias 2. So because they're DC voltages, yeah, even though we generated them, they're ground. Huh? That's right. So CGS2, you're right. So CGS2, whoops, how did that turn green? CGS2 is also not there, right? And neither is CGS3 down here, right? So those capacitors we can get rid of too. Thanks, yeah. Because this V bias is ground, so they're going from ground to ground. Okay, so that's great. That simplifies our problem even more. But before starting this, let's simplify it even more. Whether you call this a simplification or not, I'm not sure, but I'm going to do this anyway here. I'm going to take this CGD, right, which you can see is in a feedback path, and because it's in a feedback path, it's going to cause some trouble for us. And I'm going to turn it into its Miller capacitance. So I'm going to put a capacitor there and a capacitor there that represent the Miller capacitance for this. And so the Miller capacitance is CGD1 times 1 minus the gain, which ends up being 1 plus GM1 times R01 in parallel with R02. Okay, and then I also have part of this capacitance going to this end here, which again becomes 1 plus or 1 minus 1 over the gain, okay, which then becomes just the value of the capacitance there. So CGD1 ends up on that output node in shunt to ground. Okay? And so now let me write out my time constant. So I have a tau 1. So I'm getting all the capacitance tied to this node 1 here, and all the capacitance tied to node 1. I have CGS1 going from here to ground. So I know I have CGS1, but then I have that Miller capacitance, CGD1 times 1 plus GM1 times R01 parallel with R02. And all that capacitance there times the driving point resistance in shunt with this node. Looking in this direction, I see infinity. Looking in the left direction, I see RS. So RS in parallel with infinity is just RS. Okay, so that's... Yeah, CGS1 that I wrote there. So that's our first time constant, tau 1. And now I'm just going to move to the second node, which is this node right here, node 2, and write out the time constant for tau 2. So the first thing I want to do there is get all the capacitors that are going from that node to ground. And so that's CGD1, which I wrote right here. So we have CGD1 plus the CDB1 plus CDB2 plus, and now this capacitance CGD2 you can see is going to ground there, so it's perfect. It's in shunt with that node 2. Plus CGD2, and that's 4 capacitors. No, I have one more. I have CGD4 right here. See, the CGD4 is also going to ground out here, so I have to add that one. Okay, so there's 5 capacitors there. And all those 5 capacitors now in shunt with a driving point resistance at that node. What's the driving point resistance at that node? So this node right here. Exactly. So it's R01 parallel R02. That's a big resistance. Okay, so even though a lot of these capacitors, they're CGD and CDB type capacitors, which are normally not that large a capacitor. Actually, DB can be a pretty good sized capacitor, depending on how big your source drain layout. But these things plus that is going to make a dominant time constant, right? So this is probably going to dominate most of this analysis right there, just because R01 parallel R02 is a big resistor. Okay? But let's finish this anyway. Let's go ahead and get tau 3. So now I'm interested in our output node right here, and I'm interested only this time in all the capacitance that is in shunt with the output node. And so can I include CGS4 into that analysis? It's touching node 3, right? CGS4 is right here and touching node 3, but the other side of it is not grounded. The other side of it is going to the gate of M4, so it's not in shunt with that node, and I'm going to have to handle it separately. Okay? So let's just get everything in shunt with this node. So in shunt with this node is, I have a CDB3 here going to ground, which was this V bias 2. I have a CDB, whoop, that should be CGD here. I labeled that one wrong. CGD3. Okay, then plus this CDB3, and then plus the CSB4. And I think that's all the capacitors we have attached to that node there. Okay, now I'm going to multiply that by the driving point resistance at that node. What's my driving point resistance? It's everything in shunt with that node. You guys are a bit slow. Yep. So it's 1 over GM of device 4 plus GMB of device 4. It is in parallel with R03, but R03 is so much bigger than the 1 over GM, I'm just going to neglect it. Okay? And, whoops. What's that? All right, so final thing is I have to now address CGS4. And so it's going to have its own time constant associated with it. That's the capacitor right here. That's between the gate and source of device 4. And so obviously the capacitor itself is going to be involved in that. But what's the driving point resistance that I'm going to see there? So what's the expression for driving point resistance, first of all? So if you go down here to your inspection, why can't I move this inspection formula for you? It's not loaded right? Okay. Okay, so you end up with this expression right here, RB plus RE over 1 plus GM RE. Okay? And in this case, R pi, remember, is going to be infinite. This GM here is going to be a GM plus GMB type thing. Okay, because this is a bipolar equation, we need to use an MOS type equation. So let's go back here and let's write out what that ends up being here. So what's the effective RS looking that direction? Anyone? R01 parallel R02. Okay. Plus, I need the RS looking down in that direction. Louder. That's going to be R out 3 parallel R out 4, right? Because remember, you have to take into account that R out coming from 4. You have to take that guy into account. Okay? Oh, you can't see what I'm... Oh, no, I'm doing it on this side here. Yeah. And then this divided by 1 plus GM4 plus GMB4 times the resistance seen looking down this direction, the RS resistance, which was at R03, parallel R04. Okay, and now you might get worried. Resistors at the top there, right? But not really, because you got a big resistor down here, right? And so if this is much greater than 1, like before, then I can neglect that 1, and this is about 2 times that R naught up there, right? Divided by GM times 1 times that R naught. So this ends up being equal to CGS4 times basically a 2 over this GM4 plus GMB4. Okay? So that's what that ends up being. And this is small. That's a pretty small number. And so probably something you could have neglected to some extent, especially versus this one, which will probably dominate a lot of this. So in this frequency analysis, if you can see things you can neglect, go for it. Especially if you're out of time, then come back to it and maybe fix it. Or be a little more accurate coming back to it. So in the end, it's the same game. To get the final high frequency point, tau 1 plus tau 2 plus tau 3 plus tau associated with CGS4, and that then becomes my high frequency point. Yes?
On the tau GS4,
Yeah.
when you did the resistance, according to this one, it's RB plus RE, which is what you did. Why is RE in parallel? Why isn't it just looking down at R03?
Okay, because what you have in this device is actually this. Let's use this color. Okay, so this is what we have, essentially, and that's going to ground there. And so at this node, you really have an R naught of, this is 4? Yeah, R naught of 4 there. That's M4 and that's M3. And you have an R naught of 3 here. Okay? So you can think of that R naught as 4. That's not associated with this. Right? You're looking for everything that you see looking out that way. And so when you look out that way, you do see an R naught 3 parallel with the R naught 4. That R naught 4 is there.
How come on the inspection sheet you didn't include that? Because you just said the RE, just the resistor looking down. Because all that's too big
No, but see, the RE is, yeah, you're right. I mean, maybe I should have said that includes the R naught. Because the way I think of it, R naught is separate from the transistor. You could sort of do that, right? So you'll see in a lot of different books or so, people will draw it just like this. Well, they'll actually show the R naught there next to the transistor symbol. That's because you can always think of R naught as separate from the transistor symbol. And so I guess for me, it's sort of just I automatically do that. And so I'm hoping you'll automatically do it, but I guess you don't. So I'm just saying now you should automatically do that. R naught is separate from the transistor when you think of it. Okay? Yeah.
What about if R naught 4 isn't going to ground?
R naught 4, okay, so if you had a resistor up here, yeah, then things become a little more tricky, right? Then that's a situation where, depends on how big the resistor is up here. If the resistor is gigantic, then you better do a small signal analysis with the hybrid pi model or the T model again and figure out what happens in that case. If it's a tiny resistor, then you're not going to worry about it too much. But even with, yeah, so even there you'd have to include an R naught 4 coming up in that direction, but you'd have to derive what it really is, because it's not just R naught 4 now. It's R naught 4 plus that resistor and how that resistor's value is modified because you had to go through the transistor. Okay, so that would be one of those things where suddenly R naught 4 is like a feedback resistor, and this resistor above will affect it. Okay, but if the resistor is small, I would just neglect it and call it R naught 4. Okay. Any other questions about this? This is a good problem. I think it elucidated a number of different things that you may see. Okay. But this is not the last example we're going to do. Let's do one more example. Let's keep that one. Let's do one more example here. this now is a Cascode device, and I think maybe you've seen Cascode before in your 105 class. At least when I look at homework assignments from 105, I see Cascodes every now and then. So I don't know how realistic those homework assignments are, but I look at homework assignments, the subscript and the variable as capital letters. So that's V bias 3 and V bias 4. And again, the capital letters I'm using tells you that that is a DC quantity. Okay? It's DC. So in the AC analysis, what's going to happen is it's going to be grounded out. All right? And so I'm not talking about the biasing of this yet. We will talk about the biasing of this in a second. And that's where I think we'll deviate from what you actually understand already from your previous classes, is in the biasing of this thing. Because we're going to figure out ways to bias this so that you have a higher swing than probably biasing methods you've seen before. But for now, let's just do this small signal analysis. Okay, so it's small signal, so what we're going to do is we're going to take VDD, we're going to ground it out. We're going to take all of these V biases and just ground them out. Okay, because they're DC sources in the small signal AC, they become ground. All right? And so the first thing we want to do is get the gain again. No, let's first get input and output resistances. So we'll do this, but it's pretty obvious what this is. Input resistance, of course, is infinity, because we're looking right into the gate of an MOS transistor. I haven't shown you my output yet, but my output's right here. And so now I'm interested in my output resistance here, R0. Okay, and so what's R0 going to be? It's going to be the resistance I see looking up this way in parallel with the resistance I see looking down that way. Okay, what's the resistance I see looking up? That's right. I have an R0 of 3. Not plus R0 4. This is a source here. Exactly. So it's a 1 plus GM. That's right. So it'll be the 1 plus GM3 plus GMB of 3 times R0 4. Okay? That's a pretty big resistance. All right, if you look at that, that's like 2 R0s times a GM. So this GM times R0 is like a gain term. And you're taking that gain term plus 1 times R0 3. That's a gigantic amount of resistance. Okay, so I could say that that's something like a GM times an R0 squared. It's sort of on that order is what that is. And so it's enormous. Okay, that's why we like Cascode, by the way. So that's why we're doing this Cascode. That's why anyone does Cascode. Okay, and you're seeing right off from the inspection formula that that's what's happening. You're getting a huge amount of gain. What's this resistance looking down this direction? Yep, R0 2. Yep, same thing pretty much, right? So GM of 2 plus GMB of 2 times R0 1. And so again, this is on the order of GM times R0 squared. It's enormous. All right, so we have those resistances there, so I can write my expression for R0. That's just, you know, I guess to be complete, I will write it there. But that's just these two things in parallel. Okay, so that's our R0 equation there. And let's move on to get our gain equation. Now let's keep that and go this way. Okay, let's get gain now. So I want gain AV. And so to get gain, I'm going to do the usual things that I always do. I'm going to label my node. So let's call this node number 1. And this is node number 2. And the output node will be node number 3. And yeah, that's all I need, right? Because this stuff at the top is not going through the signal path, right? So I don't really need to label this node here. But I'm going to label it anyway. Let's call that node 4. Okay? But we're really just looking for everything going from V sub s through 1 through 2 to 3, which is V naught. So in the end, I can write this gain expression as V1 over V sub s times V2 over V1 times V naught over V2. I have pretty much those 3 gain stages there. And so now, point to point, V sub s to node 1, what's that gain? That's just 1, right? That's, again, a voltage divider with an infinite load impedance. Okay, what's the gain now from node 1 to node 2? That's, yeah, it's a common source, so it's basically gate to drain gain. So that's going to be minus GM of 1 times, from here to here is about minus 1. So you got no gain coming out of that. And all your gain's really coming from the second device. Okay, so that kind of tells you that in this cascode configuration, that second device has to be a good one. Okay, and that's why sometimes, you know, I remember seeing a paper on a nanotransistor using a carbon nanotube. So you guys know about making transistors out of carbon nanotubes. I remember someone doing work on this, and they had the carbon nanotube as this device, and then they used another transistor as that device, right? And then they showed that it worked fine, but that's cheating, right? Because the device that's really doing the work is your regular transistor device, not your carbon nanotube device, right? So it doesn't prove anything about the carbon nanotube device, right? So that was a published paper, and they made a lot of hoopla about it, but I'm telling you, it means nothing until this becomes a carbon nanotube device right there. Okay? Anyway, so now you know, right? Device that's important is this M2 device there. Okay, but this is what your gain ends up being here. I guess I'll write out the whole equation here with the simplification. So therefore, my gain here, A sub V, becomes minus GM of 1 times that total resistance R naught. Okay, so it reduces to a very simple equation at the end of all of this stuff. All right? Yes? This thing. So I'm going to have here CGS1, but now I'm not even going to consider the CGD1. I'm just going to immediately turn it into a Miller capacitance. So I'm going to have a capacitor here that's going to be equal to CGD1 times 1 plus the gain of this thing. But what's 1 plus the gain? Remember we said the gain was this minus 1 right there? So 1 plus the gain is 2. So that's 2 times CGD1 is what the Miller capacitance ends up being right in shunt with the input. Okay, I'm going to have another Miller capacitance on this node here. That's also going to be 2 times CGD1. Okay, so both of these here are Miller caps. Okay, so on top of this here, I'm going to have some CDBs on this node. Maybe I shouldn't be writing everything on this, but at least you have different colors, right? I'm just going to keep going with the you can see what's going on, right? CDB1 plus CDB2 are those capacitors right there. You, of course, have a CGS2 right here. And you have a CGD2 right there. I have a CDB. I guess I'll just have them off of this node right here. but that then becomes CdB 2 plus CdB of 3, and yeah, CdB of 3. I'm ignoring the CSBs right now because I guess I can at this point, except for, yeah, this one should be CSB here. I shouldn't ignore the CSBs. Whoops. So that should be a CSB from 2 there. And in this case, they're both CDBs. And I also have this, which is a CGD of 3. And then I've got some other capacitors here. So I have a capacitor here. I'm going to have a capacitor here. I'm going to have a bunch of capacitors off of this node here. Yeah, that's where I'm not labeling them. Okay, so I have all those capacitors out there, but I'm telling you now that they don't matter. Okay, they don't matter because this is a cascode circuit, and we're actually going to talk about this in more detail later. But I guess I'm just going to say that this node here, that it kind of is because it's part of the load for this thing. Okay, but just because this node doesn't move, I'm going to eliminate those capacitors. And why do I eliminate them that way? One, because it's like that node is ground. But the other thing is because if that node doesn't move, then those capacitors are not experiencing a changing voltage across them, or they're experiencing a very small one, which means they're not there. Okay? Did you have a question?
Are we generally allowed to eliminate any nodes that are not in our signal path like this?
Yeah, I would say in a general sense that would be true, but I don't want to say that completely because there might be some circuit where something might affect. Okay, because see, even though this isn't in the signal path, whoops, be careful doing that because it'll erase. Even though that's not in the signal path, it's still part of the load. So you could argue that it is part of the signal path. And so if this were not a high impedance across that, this node could be moving, and you would not be able to neglect those. Okay, so just be careful with that. But usually you're looking for capacitors in the signal path. You're right on that. Okay, so now that we've got all our capacitors, it's the same application that we've been doing again and again and again. So I'm just going to do the same thing again. So I'm going to look at node 1. Let's go to green. So tau 1, that's going to be all the capacitance that I see there. That's 2 times CGD1 plus the CGS of 1. And that's times all the resistance I see there, which is RS. Okay, and tau 2, now heading for this node right here. Again, look at all the capacitance that I see there. And in this case, right, this is a capacitor that's going from the gate of 2 to the source of 2. And usually in the past, we've seen that and said, oh, okay, that's a feedback capacitor. We have to do something. But it's not, because the gate of 2 is grounded. Right, so this is just a capacitor in shunt with ground again. And so everything associated with 2 I can call a capacitor in shunt with ground. And for 2, I guess I have the Miller capacitance 2 times CGD1 plus this CGS2, which I just mentioned is going to ground, plus the CDB1 and CSB2 capacitors, and that's it. And that's now multiplied by the driving point resistance in shunt with that node, which is, you're just looking straight up at that source there. You're looking through that source to the ground at the gate there. That ends up being 1 over GM of 2 plus GMB of 2. Okay, so that's my time constant for node number 2. And finally, time constant for node number 3. This is going to be all the capacitance out at this node here, and there's a good amount of it there. So there's going to be CGD2, you can see there. So there's my CGD2, plus all of this stuff here, CDB of 2, plus CDB of 3, plus this CGD of 3. And I think that's all of it. Yep, that's all the capacitance there. Times whatever resistance I see there, that's that enormous resistance R0. Okay? And so those are all of our tau equations. Whoops. I have run out of room, so let me stick in. And so finally, as usual, omega h is just 1 over all of these taus added together. And you could see that it was very simple to do the high-frequency analysis. We essentially had nothing in feedback after we applied the Miller effect, and we're just taking 1 over all of these taus. Okay, so that is one way to get the lowest frequency pole. Okay, so this is the dominant pole that we've got right here. And I want to ask a question at this point, though, and just ask, well, I just want to make a comment. So this is accurate enough. Okay, this actually will give you a good value for what the dominant pole is going to be. But let me ask this question. Can we be a bit smarter about this? Yeah, that's one of the things. Okay, so can we be a bit smarter about this? So exactly what was said there, right? Tau 3 dominated everything because that R naught is enormous, right? This thing here, that's huge. Okay, that means this time constant will probably dominate a lot of things. But anytime you see something like that, where one time constant just blows every other time constant away, you should start thinking to yourself, okay, so there is a truly dominant pole, but is it possible then for me to determine what the second pole is? Okay, and in this circuit, it actually is possible to determine what the second pole is just by looking at it. Okay, so that's the interesting question that we'll attack in the next lecture come next week. That in this circuit, we found the dominant pole, but we actually can extract the second pole too. And that's something we'll be spending a lot of time doing later on in class, but we'll do it next time. So I'll see you next Tuesday.